Hi and welcome to video number 10 of module 8, our last module for the HSC year, and today we are looking at ways of testing for ions. So scientists might be required to identify some inorganic substances that have been accidentally or deliberately contaminated, such as food, water or soil. Now when we're testing water quality, chemists often will need to determine what substances are present, and once they know what substances are present, they can then determine the level of those substances that might be a danger to the population. And a really current example of that at the moment is the PFAS contamination near Williamtown. And what was once considered really not a problem, they're finding that what was used for firefighting is now getting into the waterways and is making that area then really an undesirable place to be due to the contamination of their water supply and so forth. And now governments are arguing about what we need to do about it. So that's quite a recent example that we can look at. But of course there's other examples such as mercury in waterways, heavy metals, selenium and so forth that will then affect the fish and so forth that we can eat. So let's look at some examples. Now one test we're familiar with and have actually used in previous modules is the flame test. Now our flame test is a really simple technique and it's an analytical technique using the signature color that many of our metal ions possess. Now when they're heated, those atoms of the different metals will be excited and jump up one, sometimes more energy shells, and when they drop back down to their original energy shell, they emit different frequencies of light, and that is then evident in the different colors that they produce. In the table we've got here below, you can see a couple of different metal ions and their results in a flame test. So we've got barium, a greeny, apple greeny color, calcium, orange red, copper, bluey green, but you can also see here that sodium is also orange, and that can make it difficult because sodium is also that orangey red. So our flame tests are not a conclusive test there. It may be that we can do that flame test and it may present a couple of ions that we need to investigate further, but it's certainly not conclusive that that is present just by the color, as there are many different ions that will actually present with similar colors. So one of our other types of analytical techniques that we can use to determine what ions may be present in the solution is our precipitation reactions. And again, we have covered these earlier in the Year 12 and also Year 11 course. Now, for precipitation reactions, it's really essential that you do know your solubility rules. My suggestion is post them up around your room, commit them to memory. Look at mnemonics, and an example will be on our next slide. But pop them wherever you need to know them. Not only do you need to know them for this module and for testing ions, but also when we look at solubility equilibria. So our precipitation reactions are useful for finding out whether a particular anion or cation is present. And our precipitation reactions are also used sometimes to help remove unwanted substances from water. But looking here, and there is a YouTube address at the bottom of this page which introduces the NAGSAG and PMS Castro Bear mnemonic that can be used for helping us remember these precipitation reactions. But the basis of them is that our nitrates, acetates and group 1 metals, so that's our NAG, and then our sulfates our ammonium, and then our group 17, so our chlorides, bromides and iodides, are all soluble with a couple of exceptions, and those exceptions are our PMS, so we've got our lead, mercury and silver, and also our Castrobare, so we've got our calcium, we've got our strontium, and we also have our barium. That certainly covers the majority of them there. Now, the knowledge of our solubility rules can actually be used for qualitative analysis of the ions. So it will tell us what ions are present in the solution, but it won't tell us what concentrations are present in that solution. So normally what will happen is we will take a sample of an unknown solution and carry a test on that solution to remove some of the ions by precipitation. Now, if no precipitate forms, then those ions aren't actually present, and then we can use that sample to move on and carry out another test. If a precipitate does form, then you can filter out that precipitate, and we can then carry on further tests using the filtrate if necessary. So an example might be that we can see, does our water filter remove our sodium chloride effectively? And most chloride salts are soluble in, but silver chloride's not. So if we add some silver nitrate to that water, it can help determine whether the filter actually removed the chloride ions, because a white precipitate silver chloride would indicate that the filter did not in actual fact remove those ions, and you can see that in this equation below here. You've got our silver nitrate, which is what we're adding to our solution here, and if we get this formed, we know then that in fact the filter hasn't done its job. So it's handy also to know some colours of some common precipitates, and we can see these here in the table. Most of our main group metals, so group 1 and 2, will form our white precipitates. Our transition metals are where we're likely to get our coloured solutions, but also our coloured precipitates. And sometimes the colour will vary. And that can often be dependent on the oxidation state of the ion. But you can see here our solutions, that if we've got some of these metal ions in them, you can see that their solution colour is often this way, and if we mix them with any of these other anions, then we often see that a precipitate will form and what colour the precipitate will. Now, our last qualitative test that we're going to look at is our complexation reactions, and so far we've presumed that most of the ions that we'll see will exist as single ions in solution. However, that isn't usually what actually happens. Most of our metal ions in solution will become bound to another substance that we call a ligand, and that'll form our complex ion. Now, some of our complex ions are soluble, but others might form a precipitate. So our complex is formed when one or more ions will attach themselves to a central cation. Now, that central cation is usually, not always, but usually a transition metal. So let's break it down and look at a couple of these different new words that we've heard today. A complex is a combination of a metal, as I said before, usually a transition metal, and a Lewis base that has been bonded to it. So because of the arrangement that's there, the complex often has a charge. Now, that charge contains a central atom surrounded by other ions or molecules. So if the ligand, that is the ion or molecule that's attached, is a neutral substance, then the complex will often have the charge of just what the metal ion is. Now, many of our complexes produce our coloured precipitates, and that really helps from identifying what the ion is in solution. Now, our ligand is the molecule that can link to the metal atom, And again, this occurs through the Lewis base donation of an electron pair to the metal or the ion. Often we're looking at things like hydroxides, ammonia, cyanide, and so forth. So let's have a look at what this actually looks like. Here we have our metal ion, and you can see that in the center there. And we can see that we have got cobalt in the center, which is our metal ion, surrounded by the ligand, and the ligand in this case is our ammonia molecule, and it's bonding to the cobalt. Now when that all happens, that's called a metal complex, and you can see there that's represented with square brackets around the complex, and the charge is written on the outside. Now in the picture initially, that structural form, you can see in the diagram underneath that we have the same square brackets around the condensed structural formula there. So in this case, our ammonia is neutral, so the charge on the cobalt is 2+, so the whole complex will have a charge of 2+. So water is also a ligand. So if we often dissolve copper sulfate into water, the blue colour is due to the complex that's forming between the copper and the water. Now, each of our complexes have a series of characteristic colours, and we can see some of them here. So you can see copper in with water molecules will give that bluey colour there. Yet when it's with the ammonia, it'll give the purple, and with chloride, it'll give the yellow. Now this is a really good table, and you have a copy of this in your notes that helps you get some idea about what colour those metal ions will form. And you'll notice here with our iron, they're all a greeny colour, brown, a browny kind of colour for our iron 3+. This one's a bit trickier. It's got a couple of different colours, and we've seen cobalt before. So when we see the cobalt, the hydrated cobalt, we've seen that in our equilibrium reactions. Copper, as you may have seen in many cases, our 2+ copper is our blue, and again our green. And again here, not totally conclusive because we've got many without green colour. We'll have a go at our Puzzling Ions worksheet that will give us an opportunity to put this into practice, and we'll answer any further questions in class. See you then. B.